Class is started. So the quiz, there was one major note I had about the quiz. I just cannot even express how many people did this. Like 80% of the class did this. It's not an understanding thing, but it's still important. Dot means d dt only. So if your independent variable is something other than time, don't use the dot. You can use prime, okay? But where, let's see an example of, like most of the class did this. So the question was, what's ddx of u cross v? That's not equal to u dot cross v plus u cross v dot. It is equal to u prime cross v plus u cross v prime. Okay. That's going to be a super important distinction in dynamics because derivatives with respect to time give you all your relationships between position, velocity, and acceleration. Derivatives with respect to x don't give you anything on their own. You know, it's an important distinction. Oh, there was one other thing. Oh, yeah. The other thing with this problem that I saw a couple times is, so on that same problem, a couple people did this. They probably used the dot too, but I'm going to pretend like you didn't do that. U cross v is equal to u prime cross v plus v prime cross u. And that is not correct because order matters with the cross product. So when you're using the product rule with scalar multiplication, this is a perfectly fine way to do it because v prime times u is the same thing as u times v prime. But with the cross product, you can't do that. So, well, I guess I wrote it up above, but so it has to stay in the same order, like that. Okay. So last time we were talking about relative motion. And I gave you the three definitions. Let's think of it like this. There's a main definition of relative motion, and that is that the position vector of some particle P relative to coordinate system A is equal to the position vector of the particle P relative to coordinate system B plus the position vector of coordinate system B relative to coordinate system A. And the way you can remember the order of things here is fraction multiplication. So P over A is equal to P over B times B over A. Okay. If you haven't learned that yet, you'll learn it when you take Algebra 1. Okay, so from the main definition, take d dt of both sides, and you get, well, take time derivatives of all these position quantities, and you get that the velocity of P relative to A is equal to the velocity of P relative to B plus the velocity of B relative to A. Take another time derivative, and you get that the acceleration of P relative to A is equal to the acceleration of P relative to B plus the acceleration of B relative to A. And I'm pretty sure I said this at the beginning, but you got to keep in mind that these only hold for non-rotating coordinate systems. Does that mean that these only hold for inertial coordinate systems? Okay, so what's an inertial coordinate system? Did we talk about this already? All the classes blend together. Do you remember talking about that in Physics 1? An inertial coordinate system. So like basically up until this class, that's been kind of a, the idea of inertial versus non-inertial coordinate systems has been just something in the back, like it's mentioned, like, oh, by the, this works for inertial coordinate systems or whatever. All the laws of physics only apply for inertial coordinate systems. F equals ma only applies for an inertial coordinate system. And the two requirements of an inertial coordinate system are the axes can't be rotating and the origin can't be accelerating. Okay? If either one of those two things are happening, you can't use F equals ma. Well, you can see that this can be used as a fix for one type of non-inertial coordinate system. So this does apply for non-inertial coordinate systems where the origin is accelerating. And so you don't have to, you don't really have to think about this too much yet, but in this class, this is going to be an issue that's coming our way. If you have motion represented in a coordinate system with an accelerating origin, okay, you can't use Newton's laws until you correct for that. And this is the way to correct for an accelerating origin, to use this equation right here. Okay, so that's going to be a valuable thing for us when we start talking about Newton's laws. All right, so let's do an application of this. So let's say that there's a passenger running on a cruise ship, like jogging around the track on the outside. I think they have those. I've seen them in the commercials. according to the video camera on the deck of the ship, the position of the passenger is given by the function 80 times the cosine of 0.01 t. That should be 80. And then 80 times the sine of 0.01 t. According to an observer on the shore, that ship's camera is moving following the position function. P camera is equal to T, and then let's go with 0.05 T squared. So what are the position, velocity, and acceleration functions with the independent variable of time of the runner relative to the shore? Well, I'll start out with position. We know that the position of the passenger with respect to the shore is equal to the position of the passenger with respect to the camera plus the position of the camera relative to the shore. So that position function is 80 times the cosine of 0.01 t, 80 times the sine of 0.01 t, plus t 0.05 t squared. And then the other two, now this is the position function relative to the shore, so you could just differentiate with respect to time, or you could think of it as velocity of the passenger with respect to the shore is equal to negative 0.8 sine of 0.01 t, positive 0.8 times the cosine of 0.01 t, plus 1 0.1 t. So this is the velocity of the passenger with respect to the camera, and this is the velocity of the camera with respect to the shore. And then the last one, the acceleration. The acceleration of the passenger with respect to the shore is equal to negative 0.008 cosine of 0.01 t, negative 0.008 times the sine of 0.01 t, um, 0.1. So this is the acceleration of the passenger with respect to the camera. This is the acceleration of the camera relative to the shore. And the acceleration one is a really important one because the acceleration of the passenger with respect to the shore is in an inertial coordinate system. So we can use this with Newton's laws. If we tried to use Newton's laws just given the acceleration that we got from that camera, since that camera is accelerating, Newton's laws don't hold, and we get wrong answers. Okay, so this idea is going to be important when we're dealing with coordinate systems that are accelerating. Any questions about that?
If, say, the acceleration of the ship was just 0.05 t,
Mm-hmm.
t squared, could we then use the camera since it would just be 0, 0?
Yeah, right. That's right. Well, what that would mean is that you had your coordinate system moving with a constant velocity, and coordinate systems moving with a constant velocity are inertial. Okay, let's do another example. Let's do one where you have to use sort of the where you have to, move these terms around. So let's say that a passenger in an accelerating truck drops a cup of coffee. If the truck's instantaneous acceleration is 4 meters per second, 0. It's a pretty good acceleration. What's the acceleration of the coffee cup that's observed by passengers in the truck? So that's what it would be to observers on the ground. Okay? But someone in the truck, it looks different. And like when you I mean, what we're getting at here is like if you slam on the brakes of your car, everything all of a sudden accelerates forward to you. To somebody, if there's no friction, to somebody observing from outside, it doesn't look like the things accelerate at all. It just looks like the car accelerates, and those things keep going with a constant velocity. That's what we're trying to get at here. So to someone in the car, what does it look like the coffee's doing? Okay? And so the way to calculate that is the acceleration of the coffee relative to the ground, coffee ground, is equal to the acceleration of the coffee relative to the truck plus the acceleration of the truck relative to the ground. Okay? We know that this is the right order because of the fraction multiplication thing. Okay? Coffee over ground is equal to coffee over truck times truck over ground. Okay? What we know, and this is what you were saying, is we know that the acceleration of the coffee with respect to the ground is 9.81 down. Okay? So 0, negative 9.81. What?
If the car is accelerating and you dropped it, wouldn't it still be doing that?
Well, that's its velocity and its acceleration are different. If it's this is okay. So when something's in free fall, like what would happen if this room was moving 20 miles per hour that way? Which in a sense it is, I guess, because the Earth's rotating, you know. And you drop this pen, what would the acceleration be to an outside observer? Yeah, it would just be 9.81 down. It doesn't care what the room's doing. It's in free fall. Okay, so that's what's happening here. The coffee accelerating to an observer, like watching from. So if you're watching this truck go by, and somebody drops a coffee cup, it's going to look like it's in free fall. It's actually, to the observer, it's going to look like it follows a parabolic path because it has this initial velocity. But it's going to look like it's in free fall with an acceleration downwards of 9.81.
So the driver drops the coffee, then accelerates?
So this can be happening during the acceleration or whatever. The only, so when the thing is dropped, it imparts an initial velocity on the thing, but that doesn't affect the acceleration. You know, like whether something's in free fall launched this way or it's just dropped straight down, or, you know, no matter what the initial velocity is, the acceleration is just 9.81 down to an observer in an inertial coordinate system. Okay, so all right, so this is the acceleration of anything in free fall to an inertial coordinate system, to an observer on the ground. We're trying to calculate the acceleration of the coffee relative to the truck. And the acceleration of the truck relative to the ground is given. That's this is meters per second squared. So 40. And so now to solve for the acceleration of the coffee relative to the truck, now we have to subtract this vector, and we get that the acceleration of the coffee relative to the truck is negative 4 meters per second squared, negative 9.81 meters per second squared. Okay, so does this make sense with your experience? Like, say you set a cup of coffee down on the dashboard or something, and then accelerate forward. what does the coffee look like it does? Which way does it look like it accelerates? Towards you, right? And that's what this says. To an observer, the coffee isn't really in an inertial coordinate system. It's not really accelerating backwards. But to an observer in a coordinate system accelerating forward, it looks like it is. Okay. This is, so if you're trying to use Newton's laws, which of these accelerations would be reasonable to use on the right side of Newton's second law? So which one of those two accelerations is inertial? The ground or the truck? The ground. And so all of this is just what it looks like to someone inside the truck. This is the one that you would have to use in Newton's laws. Any questions about that? Okay, let's do one. This is going to come up. Relative motion is going to come up a lot with circular motion. So let's do an example like that. Okay, so let's say that there's a, what are these called? Ferris wheel? Little Ferris wheel. And let's say that it's moving at a, that it's moving at a constant angular velocity of 1 radian per second. And this is small, so let's say the radius is equal to 0.5 meters. It's like one of those little kiddie Ferris wheels outside Walmart. Okay, and let's say that now that Ferris wheel is set on the back of a truck, because someone just stole this from Walmart. And the guy's kid really wants to ride it. You know, he can't wait to get home to ride it. And the dad, being a compassionate parent, is like, okay, you can ride it in the back. Just try not to wiggle around too much, you know. So, okay, so here's the kid at a given instant riding this Ferris wheel while the truck obviously is accelerating to get away from the police. So we'll say the truck's acceleration is negative 2 meters per second squared, 0. And the truck's instantaneous velocity, so this is just a snapshot taken by the newspaper or whatever, and at this instant, the instantaneous velocity vector of the truck is, let's go with negative 20 meters per second, 0. Relative to the ground now, so say we want to come up with the velocity and the acceleration of the kid in an inertial coordinate system, so we can do the physics and stuff. So relative to the ground, what's the kid's velocity vector and acceleration vector. You want to try to do these? Yeah. All right. Good attitude. Okay, so for velocity, the velocity of the kid relative to the ground is equal to the velocity of the kid relative to the truck plus the velocity of the truck relative to the ground. We know that works because of the fraction multiplication thing. The velocity of the truck relative to the ground is, that's given, negative 20, 0. The velocity of the kid relative to the truck is omega cross r. So we have to be able to come up with the fact that omega is 1 radian per second moving in the negative z direction. That's the axis of rotation according to the right-hand rule. So 0, 0, negative 1 crossed with, what's the r vector here? It's in the negative x direction if the passenger's over here, right? That r is going from the center of the circular motion to the point you care about. So negative 0.500. And so you get a velocity vector of 0, positive 0.50. And so the velocity of the kid relative to the ground is equal to negative 20, 0, 0, plus 0.50. So negative 20 meters per second, positive 0.5 meters per second, 0. Any questions about that one?
Can you go back to R?
Yeah.
How do you find R again?
R is the vector from the center of the rotation to the point you care about. So that's R.
And it's negative because it's going out.
It's in the negative x direction.
Oh, okay.
And then for acceleration, the acceleration of the kid relative to the ground is equal to the acceleration of the kid relative to the truck plus the acceleration of the truck relative to the ground. This one is given as negative 200. The acceleration of the kid relative to the truck. This is the watermelon equation. We don't have any angular acceleration, so all that's left is the centripetal acceleration part. And so we get negative 1, 0, 0 crossed with negative 1, 0, 0. Whoops, that should be in the z direction. So 0, 0, negative 1, crossed with the quantity 0, 0, negative 1, cross negative 0.5, 0, 0. And that's equal to 0, 0, negative 1, crossed with what we got before, 0.50. And so you get a value of 0.500. And so add those two together, and you get that the acceleration of the kid relative to the ground is equal to 0.500 plus negative 200. So negative 1.5 meters per second squared, 0, 0. So the acceleration that we got for the kid relative to the truck, okay, that's in a non-inertial coordinate system because the truck is accelerating. If you use this acceleration with Newton's second law, you get wrong answers. But if you use the relative motion equations, come up with the acceleration of the kid in an inertial coordinate system. Now this is an acceleration that we could use to calculate the forces that the carousel is applying to the kid. So now if you work for a carousel, a truck-based carousel company, and you're trying to figure out what kind of loads you can expect on your carousel with a truck accelerating, and this is the acceleration you can use to calculate those forces. Yep.
But a lot of this question had to do with the kid being, on the left side.
Yep.
As it's moving, it completely.
So it'll be different. Yeah. So all those vectors will change. Those circular motion equations are all for a single instant. So if you had these as a function of time, you could calculate this as a function of time, or you could just do it at 4 different instants, and see what's the acceleration here, 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 and here. Compare, that kind of thing.
Okay.
Any other questions about this? Okay, that's it.